So what is a term which defined how the skewed dislocation and dislocation is used? That is known as the Berger vectors. This is known as Berger vectors. Okay, so what is Berger vector? Is a fundamental concept in a crystallography and material science used to describe the magnitude and the direction of the lattice distortion associated with dislocation. So what the kind of the dislocation it is and how much the dislocation and what is the distance, that all is being measured by the Berger vectors. What? Okay, so how you can measure the Berger vector? Look here. In a crystal, it provides a quantitative measurement of how the crystal lattice is misaligned due to the dislocation. First, what we need, this is the steps we need to follow to get the value of Berger vectors. The Berger vectors, which is denoted by the B vector, is a vector needed to be closed a loop around a dislocation in a crystalline lattice. Okay, first we have to make the closed loop. Here you can see. Here you have suppose A to B, B to C, C to D, D to A. Is there any misalignment? No, there is no misalignment. So dislocation line, there is no dislocation. Everything perfect. Okay. Now come to the second step. If there is no, then it's okay. But you come here in different figures. Yeah. You have moved A to B, B to C, but C to D and D to A. Is there any misalignment? No. Everything is perfect. Okay. Oh, no, no, there is a mistake. Here it is not shown clearly, but in this figure it is clearly shown. So look here. You have A to B, B to C, C to D. Now here see, it must follow the C to D like this, right? But there is a misalignment, and that misalignment is this one. Here you were the right way, you have as followed, but now you need an extra vector here, and then again it is the same way as it was earlier. Okay, now come to this way. So everything is in original way that it was, but what is the extra term? You have this part. So this part is your Berger vectors. Okay, so here in this figure you can see. Here it is also, but here in this figure it is not clearly, so we are not able to make you understand so that you can. Here it was also this red is the misalignment. Okay, this is a Berger vector, but in this figure you are not able to see exactly, but in second figure it is clearly shown. Okay, so this you can see this red vector is a your Berger vector. Okay, why? If everything would be perfect, this line must be followed. This line must be followed here, right? But here you can see this line come up to here, and then is a misalignment. That's why we have to moved up here, and then we have followed the same way. So this is the extra line, and this extra line will indicate in which direction the vector. What is the vector? Vector means they are having the magnitude and directions. Though there is a third condition also followed, that must follow the uh, vector rules, vector's law. I mean, there are the three criteria to be a vector. First one is there must be the vector must be having the magnitude. Second, the direction, and third one is follow the vector law. Okay, but in this, more or less, and in general, we are concerned about the vector which are having magnitude and directions. Okay, so the magnitude and direction will indicate you in which direction the the dislocation is and how they have dislocated from there. If we talk about here, this is the length of the Berger vector, and that length will define that how they have deviated from their own position at this particular location. If we talk about, if we will go from the here to here, and if we will take this line, then here it is the Berger line. It is the Berger vector. visible. Yeah, and that would have the different value of their arrow. Okay, the length of that arrow will be different, so the magnitude would be different. Though the sign would be the same, they have the same direction. Okay, here you can see also the same direction. If you will take this way, okay, this way, but the magnitude will would be different as you compare here. And if you are here at this particular point, then you have no uh, budget vector. Come here from here, go here, then here, and it is following the same way as it was. So it means there are no vector vector is required. It means there is no line defect in this crystal structure. Okay, so this is how the budget vector defines the dislocations. Here, the steps. I mean, first one, if there is no kind of this image, this image, okay, this figure, it means there is no such kind of the budget vector is required. It means the crystal has no line defect. Okay, but if there is, then what we need to do? We need to step. We need to follow the second step. To determine the vector B. Okay, a hypothetical closed path budget circuit is taken around the dislocation in the perfect lattice. Okay, the same path is distorted. Lattice does not close due to the dislocations. The vector required to close it is the budget vector. As I have already made you know that you have to follow the same way as it was earlier. And if there is something which is not closing the loop, then we need to close the loop, and that closing loop is the budget vector. Okay, as you can see in this image. Okay, so you have come here, 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 and this way. Now you just need to add up this one vector to complete your circle. Sorry, to complete your loop, right? So this extra vector is your merger vector. So then you follow the second step. Third, indicate the size and the direction of the lattice distortions. Simple. As I told you, I mean the vector have their direction and their magnitude. So how you can measure the magnitude? Just you need to measure the length of that particular vector. That will define your the size of your dislocation. Size of and direction, the arrow will define your direction. Okay, determine the type of the dislocation, edge, screw or mixed. What we need to do, line lies a perpendicular to the dislocation line in an edge dislocation, lies parallel to the dislocation line is at the screw dislocation. Look here. So I mean there is a line dislocation. Okay, so if the line perpendicular to the dislocation is known as the edge dislocation and is a parallel, then it is known as your skew dislocation. Look here. Here it is the dislocation. Okay, it's a parallel or this is the list. Erase it. Look here. This is your the dislocation, right? And so the movement of this whole block is perpendicular or parallel. It's just a parallel. You can see this line. If this is your uh, dislocation line defects, so whole this body is moving this side. Okay, moving this side is parallel to this or perpendicular. It's definitely is a parallel to this line, right? So then it is known as a screw. And if it would be the perpendicular like this, okay, then it would be the line edge dislocation. Here you can see in this figure. Yeah, in this figure, this is the line defects because in a perpendicular way, in this way and in this way. Okay, so here's the defect is in a line and perpendicular to that line the dislocation is moving. Okay, so that is known as your line defect or edge defect. Okay, edge dislocation. And if that is a perpendicular or sorry parallel, the parallel, then it is known as your skew dislocation. Okay, so here is a, if we talk about this particular figure, it is a skew dislocation. Okay,